but I'll speak for a few minutes with just the video on. This is actually probably not a Forth CPU, but I can make an argument that it is. And it amazes me that this seems to be the longest lasting of all the work I've done, because every year or two I get a new query about the pathetic instruction set computer, otherwise known as the PISC, P-I-S-C. And this was a result of having unsupervised students in grad school. We were studying computer architecture. I was learning about the PDP-11, and I just started working in this really nifty language called Forth. And we began to wonder, seeing more and more code. This is the era of the complex instruction set computer, the CISC, and more more and more of the application was being moved into microcode. And we thought, how do we accelerate this so that the entire application is written in microcode? And thought, well, this threaded code idea might be a way to might provide the instruction set that we need. So I hope that was enough audio. I'm going to try sharing my screen now. Screen. It would be that one. Allow.
Right, that works.
Is that coming through?
Yep.
Okay, I'll shut down the video. So we had this interesting idea, but a typical micro program machine is going to have maybe 100 bits of micro instruction, very wide micro instruction store. And we were trying to think of how could we get that down to, say, 16 bits of micro instruction. And it took a while. I kept coming back to it after years, and we finally did come up with it. Or I finally did come up with it. My friends had graduated and gone on to more productive things. So, oh, good. So what we have here, the PISC, the pathetic instruction set computer, is either you're looking at it as a microcoded CPU, by which I mean all of the bits in the instruction are controlling hardware signals. They're not packed into some efficient utilization of the memory. Each bit is a hardware line. So this is either a microcoded CPU with a very short micro instruction, a 16-bit micro instruction, which, as anyone will tell you, is pathetic. Or it can be viewed as, forget the micro instruction, it's a hardwired CPU. There is no micro instruction store separate from the main instruction store. A hardwired CPU with a very peculiar instruction set, or in other words, pathetic. So that led to calling it the pathetic instruction set computer, which is, I think, probably the most idiotic instruction set of any computer I've ever seen. It has no branch or conditional branch instruction, for example. It has no way to rotate or shift right, and it can shift left, but to rotate left, you need multiple instructions. There's no subroutine call, but in a threaded Forth environment, you don't need a subroutine call. You're doing it all. It's the same reason that Forth works fairly well on an 1802, and other languages don't really work well with that processor. So what I came up with eventually was this. That's it. That's the entire central processing unit. It's got a 16-bit ALU. It's got a 16-bit register file with 8 registers, and an instruction register, and some glue logic, some additional functions. You will note the absence of a program counter. The program counter is register 7 in the register file. There's the PDP-11 influence. And the microinstruction word is very simply reading from bit 15 down to bit 0. There's a memory read strobe, a memory write strobe. Those go out to the external memory. A reg, which selects one of the registers in the register file. It selects the A address, which is input only. That's a very strange register file. It's either viewed as a 3-port or a 4-port register file, because we can read one register, write a different register, and both read and write a third register. So 3 bits to select the A register, which is named after the ALU, in this generation named after the ALU port that it's using. 3 bits for the F register, which is where the F output, the function output of the ALU is going. A ST is the instruction to latch the status resulting from this instruction. The CYN is a 2-bit selector because the carry input to the ALU sometimes needs to have a carry if you're doing multiple precision arithmetic, but also sometimes need to have a forced carry or forced 0 bit or a forced 1 bit. So, and to read it as a status register, or sorry, to read the status back into the ALU, I also have the A equals B as one of the choices for the carry input. And then the ALU function itself is 5 bits. Those are just 5 bits of the 74181 ALU. Now, how does this thing work? It alternates between a fetch cycle and an instruction cycle, where the instruction cycle comes from the program. The fetch cycle is hardwired and does this. Address register 7 is output to the A bus, which is the address bus. That also goes into the ALU. The ALU has a function of A plus carry. And if the carry is forced to be 1, that's A plus 1. And that's your auto incrementer, your increment of the instruction counter, or the program counter, excuse me. So the ALU increments register 7 by 1, and simultaneously the register 7 is output to the memory. The data from the memory goes into the instruction register. Now, with one small change, this is hardwired. This is not a part of your application program, but with one small change, it is a part of your application program. It's the memory read function. And memory read is the exact same thing we just did, except instead of going into the instruction register, it goes to the C port on the register file. And this actually is the tiny little bit of onboard hardware that isn't being done by micro instruction bits. Arguably, it should have had 17 bits of micro instruction because there's 2 different functions being used here. One is the store function for the instruction register. The other one is the store function for the R7 in the register file. So I cheated to the extent of 1 bit. This also can be memory read with post increment. That's in fact what you see here now, the A plus 1. So if you want to traverse a table or move up and down a stack, there's a post increment function. And it can be load immediate in exactly the same manner as the PDP-11. Use register 7 as the address register in your own instruction. Cause the ALU to increment it, but the data is stored into the register file rather than into the instruction register. Proceeding. No, wrong button. There we go. Then there's the memory write. Again, the address side of this is totally unchanged. In this case, comparing with the previous one for a moment, looking at the 4-to-1 multiplexer at the upper right, and I got it wrong there. I didn't actually program the post increment. So that is a memory read without post increment, and this is a memory write without post increment. And the difference is we're putting a 0 into the carry input instead of a 1. And with the memory write instruction, the C register of the register file is read out of the register file and written to memory. The C register address, the address selector for what that port's going to use, is always 0. So register 0 is the memory data register in both directions. You want to write memory, you have to put the desired data into register 0 and then do a write instruction. You want to read memory, you do a read instruction, and then you have to get your data out of register 0 into one of the other registers, which actually is just another instruction. Oops, there. I'm actually going to come back to this. Well, no, I'll stay with the order I chose. ALU functions that don't require memory access. This is an example of a single operand ALU instruction. It's output from the B port, fed into the ALU, and possibly combined with the other B port, the other ALU port, but we'll get to that. And in this example, I've just chosen the one of the 16 functions available for arithmetic functions on the ALU, and that's A plus carry. And if you think about that, that's a left shift and bringing what the Z80, I think, used to call the left shift through carry. I may be misremembering that, or excuse me, rotate through carry. But this shifts the ALU one place to the left and then brings whatever the carry is into the lowest bit. There are several such instructions there. You can do two's complement. You can do logical inversion shift. You can clear a register all through ALU functions. For dual operand ALU functions, this is the data path, and this is an addition with carry, add with carry. The B register on the register file is output to the bus, and that goes to the ALU. The C register of the register file, which is normally a different register, is output to the data bus, the D bus. That also goes to the ALU. And the result goes back in and replaces that first register. So if I'm, because, well, actually it doesn't have to. Sorry, I'm thinking ahead to the next generation. Sure, I'll come back to that in a moment. But the third register is output and stored in the register file. So that right there is the add with carry. And of course, to add without carry, you simply select that the carry is 0 instead of the carry input to this part of the board. So that's what it looks like. I actually found this in a desk drawer before this talk. And everything to the, not to the left of the center line, including those two small chips and the parts, is the processor. Everything on the right side is the memory and the I/O. It takes a 2651 UART. And it also talks to a very peculiar video display that I have that plugs into that edge connector. If you look closely, I don't know how this appears on your screens, but the date on those EEPROMs is September 11th, 1993. That's the last time I've tested this unit. And I'm curious to see if the EEPROMs have held the data. But because there's a lot of testing still to be done to make sure this survives storage, I didn't think I was going to have it for today. I am working on a simulator for this board. I have a software simulator for what is currently the PISC-1 and is what is going to be the PISC-1A, and eventually I may carry it into the next generation. But that's it. I can't do it. No, I don't think the pointer shows up when I do it this way. If the pointer is showing, and I can't tell because I'm looking at my original, the registers over here, the chips over here on the left edge are the ALU, and the next two columns of chips are the register file. So that leads us to some weird instructions. But let's talk about a couple of Forth primitives where we arbitrarily have decided the PC, the program counter being 7 and the memory data register being 0, those are forced by the hardware. The other four are arbitrary choices. The instruction pointer for threading, I've used register 6. Return stack pointer and parameter stack pointer are 3 and 2, and the temporary register W is register 1. And for next is 3 of these instructions. There's a memory read cycle that uses the IP as the address, also stores the updated A+1 value back into IP. So that's use IP as the address for the read, and then increment that and store that back into IP. The second instruction in next is another memory read, except now the data is what you just read. Since we're reading from a thread of 16-bit addresses, the data register is used to provide the address bus, and what is read back goes into the W register. And I have actually, I believe it. Well, anyway. And then finally, that data, which is another address, this is indirect threaded code. That data is read into the program, or copied into the program counter, and there you go. You've started your next word. Skipping do colon for a moment, I'm going to save some time and not talk about a couple of these. I left as an exercise for the student, as we used to say. The exit function is memory read from the return stack. So use the RP register as providing the address. Increment that address because it's a push down stack and store the incremented address back into RP. So that basically pops the return, whatever is on the return stack, the topmost item, into the memory data register and then continues. And the next instruction, MD address, memory data register provides, which we just read from the return stack, provides the address for the next instruction. That is not a memory read cycle. Notice there's no MRD in that leftmost column. This just is copying the memory data register into the IP register. So memory data source, IP destination, and just copy with no other function, just A. A is a function of the ALU, and then we're prepared to do the 3 instruction next from above. I think I could bore you to tears going through more of the instructions, so I'll just leave it at those for the moment. Now, I talked about a tweak I wanted to make. Why I'm not entirely satisfied with that. It occurred to me after wire wrapping this prototype, and it's a lot of wire wrapping, it occurred to me that what I really could do is, rather than forcing all memory operations to go through register 0, I could make the data register, and that's deceptive because it's not, they're all address and data registers. This is not like a 68,000 where you have different functions. This is a PDP-11. Any register can be used for an address or a data. But the register on the D bus is how you should read data reg or DREG. The register output on the D bus is specified by 3 bits of the instruction word, and the address, the A and B now are specified simultaneously with the A reg field, three other bits of the instruction word. I have not yet tested this or implemented it. I haven't done the hardware, certainly. I was going to do this as a printed circuit board, but never got around to it. And I'm going to implement this with the simulator as soon as I get the simulator for the original version working. This actually can save a few instructions. I've coded a few primitives, and this can save a few instructions. So this is going to be the PISC 1A. I don't think it merits a 2 yet. So that is the quick rundown of the pathetic instruction set computer and how it works. Are there any questions?
I have one. I noticed you got 2 separate bits for read and write. What happens if you set both of them? Will you create a short on the bus?
You won't create a short, but I don't know how the memory chip would respond to that if you try to do read and write simultaneously. Oh no, you might create a short on the data bus because no, that's one output, one input. I'd have to think about that actually. If you do memory read and memory write, I'll have to look at the circuit diagram, but I think there might be a short here, not in the memory chip, but here. I think the buffer will try to drive the data bus at the same time as the register file is trying to drive the data bus. Probably a short.
It may be worth having 1 bit for enable, memory enable, another bit for read or write to be a bit safer.
Yeah, that's the problem. That's that 17th bit that I wanted to avoid using.
No, you use the 2 bits. So instead of memory read and memory write, the bit 15 is enable, memory enable, and bit 14 is, if it's 1, it's reading, if it's 0, it's writing, or vice versa.
So you've implemented your own halt and catch fire function.
So you can have your tri-state then. You can either read or write, or you can have memory at all.
That makes sense.
Yeah, the register file. The register file and the buffer can both be tri-stated. And the question here is it worth adding logic to prevent that from happening? And maybe it is. We actually have 4 signals on the board. There's memory read, which goes to the memory write, which goes to the memory. Read enable C, which is to enable that output on the register file, and write enable C, which means that when data is available on the data bus, that at the end of the cycle, that will get written into the C register.
If it's possible to do a short, so as soon as your program crashes, you might be executing the code. It isn't real code. You don't want your machine going up in smoke.
Yeah.
Yeah, that's a very good point, and I should tell you,
Mhm,
I should
mhm, mhm.
design another safety element into that. Yeah, that's a very good point. As long as I'm designing, as long as I'm revising the design, I might as well do that too.
It's only for brave programmers.
There was somebody else there.
Yeah. Brad, had you thought about having an FPGA implementation of this?
I have since. In 1993, I wasn't thinking that way.
Mhm.
I was doing well to have wire wrap. But every time I look at this and say I should do this in FPGA, I think, why? Because I can do much more with the FPGA than I'm doing here. This was an exercise in how much can I do with the smallest number of 7400 series chips.
Yep.
And I believe the total chip count is 22.
Mhm.
So that was one of the goals. And again, I was a college student. I didn't have the ability to, I didn't have the money to do FPGA. I know it's
yeah.
very expensive now.
It's very expensive
now, but
today.
Sorry?
I kind of want to try it on this now. See if I can do it with FPGA.
Oh. Yeah.
Yeah, I mean, there is some advantage of low gate count CPUs, even on FPGAs. You know, we've got specialist, you can use them as sort of specialist processors. Obviously, a lot of the big FPGAs have got, you know, you can fit on a massive number of gates, but it's sometimes an advantage to have a very small processor, general purpose processor, implementing a few gates on a FPGA. So there is effort still to have reduced gate count general purpose processors.
Mm-hmm. I've got a computer here that actually is implemented in TTL logic, and it's very, very simple CPU, and it runs code that emulates a more advanced CPU.
Mm-hmm.
So it runs more advanced software through it, almost emulation, which is an interesting approach.
Sure.
By the way, I think it was John Ribel who, at the very same Silvermar conference, the formal conference that used to be held every year out in California, at the very same conference where I presented this, he presented his machine, which was remarkably similar, except he did it with an FPGA. And he didn't have some of the ridiculous restrictions that I've required, such as, you know, no conditional jump instruction.
I see.
But he got the gate count down to, it was on the order of 2,000 gates, which is what this is. This is also on the order of 2,000 gates. I guess I should unsave this and go back to video, which is done.
Well, how does it make?
How do I stop sharing? Oh, there it is.
I really enjoyed that talk. That was
with any luck.
As someone who's trying to design my own CPU
thanks.
on an FPGA, I found that really fascinating. The simplicity of it. It felt really, really elegant.
Yep.
I enjoyed hearing that. Thank you.
I also spent many university days designing 16-bit simple RISC CPUs. It was a fun occupation. Didn't do anything for my studies, of course, but.
Are there any other questions to Brad?
Well, I just have two.
Go ahead.
I'm not sure how the PISC would make decisions. How would you do something or something else? And the second question is, how fast can you clock it?
The clock rate is limited to 5 megahertz, I believe, if I recall correctly. Yes, I have a 10 megahertz oscillator and I divide it by 2. You make decisions in conditional branches as follows. There is a way using just arithmetic instructions to propagate the carry bit through the entire register. It's basically a function which is 0 minus the carry bit. I think actually the function is 0 plus 1, or excuse me, register, never mind. 0 minus the carry bit is the ultimate output of that. So you can, from the carry bit, looking at the carry bit input, you can turn it into all 0, the register into all zeros or all ones, depending on the status coming in. And then you AND that with the branch offset, a relative offset. So now you've got either 0 or a relative branch offset, and you add that to the program counter. So with 3 different arithmetic and logical instructions, I can do a conditional branch.
Right.
Fortunately, it has to be relative addressing, but yeah, a lot of systems.
It reminds me,
the genius
Does that
of
answer the question?
it reminds me of that compiler that only outputs move instructions.
Yeah, you can do similar things doing absolute addresses. That works.
It can be done with absolute addresses, yes. It's just a trifle more complicated.
You could read an absolute address from memory anyway, so that's exactly how the ARM does it. When you read, you can read. If you're trying to fit an address in an instruction, you can. So you have to do relative, and the relative points to another address which holds the actual full 32-bit address. See.
Oh yes, I've actually seen that in the code I sometimes generate for the ARM.
Right.
Hi, Brad. When I came across the PISC online, I was very impressed, with the beautiful simplicity of it. And I'm a machine using AMD 29705s along the similar principle. I've actually got here, I've just dug it out beforehand, a tube with 8 74172s, 1977 date codes on them. This is a piece of unobtainium here, quite a number of years ago. Ones that someone else sold me. It's a long-standing project I've never got round to doing, but I was thinking of making something with this real chip. I think I'd have to test these chips first before investing too much time in it. But it's a rare chip. When you look in adverts in old magazines at the list of TTL devices, it always used to be the most expensive one. And it must be one of the rarest, I think.
They are rare.
Sure.
I have no idea what. I've sometimes suspected that chip was designed to build the PDP-11, but they are very rare. I get queries with some regularity about, I want to build this, but where do I find the 70? Design to use a different register file chip. And you mentioned the AMD 2900 series. I don't know how available those are. I have a tube full of those. You have a tube of 74172s. I have a tube full of the AMD parts, which I was thinking someday I would use for a different microcoded computer, but that's one of those never got around to it projects. I think this one's going to require Peter's going to be happy to hear this. This is going to require a follow-up report. I have to get this working. I have to get the simulator working. I have to get the 1A modifications made. And then I have to start, and then I have to get the simulator working. So come back and talk about that. And I have to start looking at the different chips for the register file. So, Peter, you're going to have to schedule a follow-up with me in a year or so.
Very good.
Seems to be about the speed I'm moving.
Very
Absolutely. Good. Yes. We love it, Brad. And you see, with each of our demos, we call these demos a short presentation. We generate a lot of enthusiasm in the FOSS community all over the world. We have people talking from Canada like Brad, and we have George in Japan, and we have people everywhere that want to learn new stuff. We have young programmers also in the group today.